In this video we're going to look at collision theory, and actually I'm going to combine lesson 2 and lesson 3 because ordinarily when we teach this there would be a practical in both of those lessons, but obviously we're not going to be able to do that. So to make it worthwhile, I'm just going to roll the two lessons into one. So when it comes to collision theory, if you remember from the previous video, what two factors affect the rate of reaction? And the first one is the frequency of collisions of our reactant particles, and also the energy of these collisions. So anything that increases either the frequency of the collisions or the energy of the collisions is going to increase the rate. You don't have to increase both. You can just increase one of those and it will increase the rate. So we have to talk about a variety of different conditions we can change in a reaction and the effect they'd have on rate, and be able to justify them using collision theory. The first one being temperature. So here we have two diagrams, one showing a system at low temperature and one showing a system at high temperature. So if we increase the temperature by adding heat energy, our particles are going to have more kinetic energy, which means they're going to be moving around faster. And if they're moving around faster, and they're still in the same sort of fixed volume, but they're moving around with more energy, number one, they're going to collide more frequently, and you can see this quite clearly. If they're moving with more energy and they're moving faster and they're moving more, they're going to collide more frequently. But also, because they've got more kinetic energy, when they do collide, they're going to have more energy. So actually, increasing temperature is definitely going to increase the rate, because by increasing the temperature, the particles have more kinetic energy, they are going to collide more frequently, and they're going to collide with more energy. So here we have what we call the disappearing cross reaction. Now this is one of the reactions you need to know, and it is one of the required practicals which we will get round to either doing or at least filming. And it's a very simple reaction. It's sodium thiosulfate reacting with hydrochloric acid. So hydrochloric acid plus sodium thiosulfate, and the products of this are sodium chloride, sulfur, sulfur dioxide, and water. And if we add state symbols to that, aqueous, 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 solid, gas, liquid. Now normally we would look at that and say, right, okay, we've got a gas product, so we can measure the mass decrease over time, or we can look at collecting that gas and measuring its volume over time. But the problem with this reaction is that sulfur dioxide just immediately dissolves into the water and forms sulfuric acid. So we can't measure it, we can't collect it, the mass won't change. But what we do have is solid sulfur being produced. Now both of these are colourless solutions. Everything here forms a colourless solution, apart from the solid insoluble sulfur. So the more of this that gets produced, this solution here is going to start going cloudy until there's a point at which you can't see through it because there's too much solid sulfur in the way. So that's why it's called the disappearing cross reaction. You set it up just like this, you put a measured amount of sodium thiosulfate or hydrochloric acid, it doesn't matter which way round you do it, you put a measured amount in the conical flask and then you add the other reagent and you start the stopwatch, and you simply wait looking through the top of the conical flask, and you have a cross drawn on a piece of paper underneath, and you just time how long it takes until you can't see that cross anymore, and then you stop the stopwatch. And then you just repeat the experiment using different samples of thiosulfate or different samples of hydrochloric acid. that you've kept at different temperatures, maybe by putting them into a water bath. So you could try it with room temperature hydrochloric acid, and then you could try it with hydrochloric acid that's been in a water bath at 40 degrees, and then you could try it with hydrochloric acid that's been in a water bath at 50 degrees. And you'll be able to compare how long it takes for that cross to disappear. Now, if the rate is increasing like we expect it to, if we used a higher temperature of the reaction, then it will go faster. So it will take less time before you can't see that cross. Now, we're talking about this reaction in terms of temperature, but it doesn't have to be temperature you vary. The method can be altered to investigate concentration, for example. We could set this up exactly the same, put a measured amount of sodium thiosulfate in and a measured amount of hydrochloric acid, and time how long it takes for us not to be able to see that cross, and then we could repeat that experiment using different concentrations of hydrochloric acid, and we could investigate the effect of concentration on rate of reaction. So this is a generic method that you must know. You need to know the disappearing cross reaction, you need to know the setup and the method, because you will be asked to describe it. And you might be given it in the context of investigating temperature, but they might give you the context of investigating concentration instead, which is precisely what we're going to use this reaction for in the required practical. So the method doesn't change, you're just varying which independent variable you're investigating. So this is disappearing cross reaction using color change to determine rate of reaction. So just to recap here then, so at a higher temperature, our particles have more kinetic energy, they collide more frequently with more energy, therefore increases rate of reaction. Okay, so whenever we're justifying whether something increases or decreases the rate of reaction, we must talk about the particles and collision theory. So high temperature increases rate of reaction because the particles have more kinetic energy, they collide more frequently with more energy. So we've used collision theory to justify why the rate has changed. So like I was saying in the last video, a lot of the time in this topic you're going to be having to draw graphs, annotate graphs, and analyze graphs. So here we have some results from an experiment where we varied temperature and measured the time taken for the cross to disappear. So as we expected, as the temperatures increased, the time taken for the cross to disappear has decreased because the rate of reaction has gone faster. Now at the moment we have temperature and time, and if we want to look at the rate, if you just do 1 over the time taken, that will give you the rate, because 1 over time gives you per second, and remember, rate is always measured as something per second, grams per second, centimeters cubed per second. So we didn't actually need to measure anything. As long as we can convert it to per second, then we can look at the rate. So we can convert all of these times to rate by just doing 1 over the time. So 1 over 160, 6.25 times 10 to the minus 3, 1 over 40, 2.5 times 10 to the minus 2, 1 over 20, 5 times 10 to the minus 2, 1 times 10 to the minus 1, and 2 times 10 to the minus 1. Now, these are very small numbers, and it's not particularly easy to plot them on a graph when they're this small. So what we're going to do is just multiply them all by 1,000 to make them all into whole numbers, or into bigger numbers. It's going to be much, much easier to plot. Okay, so times in this by 1,000 is going to be 200, 100, 50, 25, and 6.25. And these are going to be much, much easier numbers to plot. That's the only reason we're timesing it by 1,000, to make them easier to plot. So we're going to plot temperature against rate, and we're going to use the modified rate because it's going to be easier. So we should know that our first axis, the thing that was being changed, the independent variable, that is our x-axis. This is going to be our y-axis. So on the x-axis, I've got 1, 2, 3, 4, 5, 6, 7 large squares, and I've got to get to 55. So 55 over 7 is going to be 7.8. So I'm going to round that up, because you can't round down. I'm going to round that up to 10, and I'm going to go up in tens. Might as well go all the way. And my y-axis needs to go as high as 200, and I've got 1, 2, 3, 4, 5, 6, 7, 8 large squares to do that. So 200 over 8. So that's a nice round number. I'm going to go up in 25s. So we have temperature down here in degrees centigrade, and we have rate times 1,000 seconds to the minus 1. So now we can plot this. So at temperature 5, the rate is 6.25. So it's going to be sort of here, isn't it? Just about there. At temperature 25, the rate is 25, so that's nice and easy, 25, 25. At temperature 35, the rate is 50. At temperature 45, the rate is 100. And at temperature 55, the rate is 200. So again, we've got a curve. So in order to draw the line on that, I'm just going to turn the page so that your hand is on the inside of the curve. Okay, it makes life a bit easier if your hand is on the inside of the curve. And I'm going to do my best. I'm going to commit to it. I'm going to do it in pen. I believe in the method. And I'm going to hopefully get a nice smooth line of best fit. Okay, obviously you would do that in pencil, because if it goes wrong, see, if that had gone wrong, I would have had to stop this video and start again. But do it in pencil, but a nice smooth line of best fit. And what we can see from this graph, as temperature increases, rate of reaction increases. It is not linear. Okay, so I'd say rate increases exponentially with increasing temperature, because our particles have more kinetic energy, they're going to collide more frequently and collide with more energy. Therefore, they're going to have more successful collisions, because not all collisions are successful. Sometimes particles collide, but they don't have the activation energies. They just bounce off of each other. Only collisions that have the activation energy actually react and form products, and we call those successful collisions. So increasing the frequency of collisions is obviously going to increase the number of successful collisions. If you increase the total number of collisions, then you'd get more successful ones as well as more unsuccessful ones. And if you increase the energy of those collisions, then you get more successful collisions in total. So you can see that very clearly. Our rate of reaction is increasing exponentially with an increase in temperature. Another thing we can look at is concentration. Now, it's important that you are able to define concentration. Right? Concentration is the amount of a substance or the amount of particles in a fixed volume. And if you don't mention that fixed volume, then you're going to lose marks. So concentration is the amount of a substance or the amount of particles in a fixed volume. And that's why if you think about all the units for concentration, it's moles per decimeter cubed, grams per decimeter cubed. It's all per decimeter cubed or centimeter cubed. It's per unit volume. So we're going to draw a dilute and a concentrated solution here. So we're going to have our solvent particles. I'll try to draw the same over here. So the volume of both of these boxes is exactly the same, and the number of solvent particles is exactly the same. But if I have a dilute solution, I will have fewer particles or molecules of our substance in that fixed volume. Okay, it's just like when you're making a drink of squash. You know, if you have very, very dilute squash, you haven't put very much in. So you have less particles of Ribena per unit volume. Whereas if you make it really concentrated, you've got more particles of Ribena and it's more concentrated. So a more concentrated solution is simply going to have more particles of our substance in the same fixed volume. Okay, so there's no point just saying it's got more particles or it's got more molecules in it, because if you don't specify the volume, then it's not really the same. It's kind of like if we were back in the lab and I moved the class to the hall, we would have a lower concentration in the hall. Same number of students, but we'd have a lower concentration because the volume of the room is increasing. So the number of students per unit volume would actually decrease, even though none of you have disappeared. So the unit volume is really important. So in our more concentrated, we're going to have more particles of our substance or of our, whatever we're talking about in this case. So use the diagram above and collision theory. Predict and explain how change in concentration will affect the rate of reaction. So increasing the concentration means more particles in a fixed volume. So what's the significance of that? If I've got more particles in that fixed volume, now imagine that you were in a room, all of you, and you were blindfolded and you were walking around, you'd bump into each other. Now, if we repeated that, but there was twice as many of you in the same room, you would bump into each other more often. So the frequency of collisions will increase. Now, what doesn't change is the energy of those collisions. We've not given the particles any more energy than they already had. So we're not increasing the energy of the collisions, and we're not increasing the number, the proportion, I should say, of successful collisions, all we're doing is increasing the frequency of all collisions. So if we say that there are 10 collisions and for every 10 collisions one of them is successful, well, if we increase the frequency of collisions so that there's 20 collisions, well, then there'd be 2 successful ones, so we'd increase the rate. So increasing concentration means more particles in a fixed volume. Make sure you talk about volume. The frequency of collisions increases, therefore the rate of reaction increases. So there, very simply, we've spoken about the effect of temperature on the rate of reaction based on collision theory, the effect of concentration on rate of reaction based on collision theory. And what you can now do is answer these exam questions onto page 104, and the next lesson we'll do will be on surface area and rate.